In this video, we're going to introduce and talk about exponential functions, which you've probably seen before in an earlier math class. So why don't you pause, copy this example down, and then I'll fill in the details. Right. In example one, we have that a town with a population of 1,000 people in 2020, and it's experiencing a constant 5% growth rate each year. And we'd like to come up with a population function, P of t, for the population at time t, where t is in years and t equals 0 corresponds to 2020, okay? So I'm just going to sort of fill this table in and hope to see a pattern that I can then write a function based on that pattern. So at time 0, well, that's 2020, and we knew our population was 1,000. Okay? All right. 1 year later, apparently our population has grown by 5%. So 1 year later, I have that 1,000 that I had before, plus it's grown by 5% of 1,000. Okay, so I'm going to add 5% more people. And I'm going to simplify this slightly. I don't want to crank out the number. I want to sort of see a pattern. So I just want to simplify it a little bit and leave it alone. So I note that I've got 1,000 there and 1,000 there, and I could imagine that I have a times 1 here. Okay, so what I could do is I could factor 1,000 out in front. And that would give me 1 plus 0.05. Or if I like, it's 1,000 times 1.05. Right? And hopefully that makes sense. We have 105% of the initial population after 1 year. Okay. All right. Well, let's move on to year 2. So year 2, I get 5% bigger than this. So I have my population that I had at time 1, 1,000 times 1.05, plus that 5% more, so 0.05 times that population from year 1, 1,000 times 1.05. Okay, so population I had last year plus 5% more of it, right? And again, I'm just going to simplify a little bit. I'm going to factor out in front the 1,000 and the 1.05 because that's common to both piles there. So I have 1,000, I have 1.05, and what's left over is that 1 plus that 0.05. So it looks like I've got 1,000 and a 1.05 times 1.05. So that's a 1.05 squared. Okay. All right, let me do that one more time for year 3. So in year 3, I have the population I had last year, which was 1,000 times 1.05 squared. And then I get 5% more of that population. So here's my 5%. And here's that population from a year ago, 1,000, 1.05 squared. Okay. So again, I'm going to factor the 1,000 and the 1.05 squared out of these two pieces. And I can imagine a times 1 there. So I've got 1,000, a 1.05 squared. And what's left over is the 1 from the first term and a 0.05 from the second term, which would give me 1,000 times 1.05 cubed. Okay. All right, so I'm getting a pretty nice pattern. 1,000 times 1.05, 1,000 times 1.05 squared, 1,000 times 1.05 cubed. And so I think the pattern's perfect because I think I could have gone back here and said, hey, look, this is 1.05 to the 0th power, which is just 1, right? But times 0, power 0, time 1, power 1, times 2, power 2, times 3, power 3. So I think in general, at year t, the population is going to be 1,000, 1.05 to the t. And we call 1.05 our growth factor. Okay. All right, let me do another one like that, but maybe a little bit faster. So why don't you copy this down and I'll fill it in. All right. So starting in 2015, I invest $10,000 badly because each year I'm going to lose 3% of whatever I had the year before. So my investment is constantly going down. And I'd like to determine the amount function, so A of t, the value of my investment after t years. And I'll say t equals 0 is at 2015 when we started. All right, well, because of that, 2015 times 0, I knew I started with $10,000. Okay. All right, 1 year later, I lost 3%. So I had $10,000 and I lost, so I subtract 0.03 times 10,000. Okay, and I'm going to play the same game. I see a 10,000 common to both terms. I could imagine a times 1 in there. So I can factor out a 10,000 that would have 1 minus 0.03, or in other words, 10,000 times 0.97. Okay, so that's what my investment is worth after 1 year. All right, well, 1 year later, my investment a year ago was 1,000 times 0.97. And now I'm going to lose 3% of that. So subtract 0.03 times what I had a year ago. Again, I could imagine a 1 sitting there. So now I can factor out the 1,000 and the 0.97 from both terms. And when I do that, I've got a 1 minus a 0.03. So it looks like I've got, oops, not 1,000. That's 10,000, isn't it? 10,000. Squeeze an extra 0 in there. Ooh, ooh, my bad. All right, so it looks like I've got 10,000 0.97 times 0.97, or 10,000 times 0.97 squared. Okay. All right. Well, I can play the same game again, but look, it looks like I've got 10,000 times 0.97 to the 1 after 1 year, 10,000 times 0.97 squared after 2 years. And I think the same thing would happen after 3 years. And hey, I could think of this as 0.97 to the 0, just so 0, 0, 1, 1, 2, 2. It all seems to correspond nicely. So I think my amount after t years is that 10,000, and then hit it by 0.97 t times, 1 for each year of losses. And I call that 0.97 my decay factor. Okay. All right. So I pause, copy. So what we've seen is that in general, a function of the form a times b to the power of t models situations where a is our initial amount, initial population, initial investment, and b is our growth or the decay factor, as the case may be. We also call b our multiplicative factor, all right? In general, some vocab, if I just have a function that's b and some number b to the power of t, we call that an exponential function. So like f of x equals 5 to the x. That's an exponential function. And then a function like the one I dealt with up here, a times b to the t, that's called an exponential growth or decay function. It includes an initial population or an initial amount, right? All right, so let's look at example 3. Unfortunately, we got a cancerous tumor that starts with 200 cancerous cells. The number of cancerous cells is doubling every day, all right? And we want to determine A of t, the number of cancerous cells after t days, okay? Well, so the initial amount is 200. And it looks like we're growing and we have a growth factor. Growth factor looks to be, it's doubling every day. So our growth factor is every day I'm going to multiply yesterday's number of cells by 2, okay? So It's growing pretty quickly. It's 100% growth rate, all right? So with that, I can say the amount of cancerous cells I have after T days, did say T was in days, yep, T days, is my initial population of 200, and then I'm going to multiply it by 2 raised to the T power. So if it's 5 days, I'm going to double 200. Well, 200 is going to double 5 times, 200 to 400, 400 to 800, 800 to 1600, etc. Okay. All right, so there's my exponential growth model for this. All right, last but not least, pause, copy, play. All right, so you invest $800 at time 0, and every month you get 1.5% growth. It's a pretty good investment, right? And we want to determine how much the investment's worth after 2 years, okay? So I've got an initial amount of 800. I'm growing, so I've got a growth factor, or my multiplicative factor, but let's say it's the growth factor. We're growing by 1.5%. So like if I get a little confused here, after 1 month, I've got 800 plus 0.015 times 800, right? That's how much I'd have after 1 month. Initial amount plus 1.5% of it. And I could pretend there's a 1 there. And if I factor my 800 in front, I would have 1 plus 0.015, or 800 times 1.015. So it looks like 1.015 is my growth factor. Every month I have 101.5% of what I had a month ago, because I grew by 1.5% and I didn't lose anything. So my growth factor would be 1.015. So if T is in months, which it should be because my growth factor is in months, the amount I have after T months is going to be 800, 1.015 to the T power. And I'm looking for how much I have after 2 years. So that's time 24 months. So if I plug in 24, I would have 800, 1.015 to the 24th. And I cranked this out in a calculator, and I got, after 2 years, your investment is worth $1,143.60. All right.